Year 12 and Year 13. This is the second part of the second practice task for the trig internal, and this is the part where we have to look at the red and the blue functions and figure out general solutions for where they meet. Okay, so we've found the equation of the red curve, and we decided that that was y equals 5 sine x plus 4. Okay, that's a 5, not an s. And we have to equate that with this function here, and we have to find the possible values of x for which those two functions have the same value. And I'm going to come back and also find particular solutions here. Now, one of the reasons to do that is that we can see just from looking at those two graphs roughly what those numbers are, right? So this is just over 2/3 of pi, so that's going to be 2 point something, and this one is just below 2 pi, so that's going to be 5 point something. So they're the numbers that we're wanting to get out of my general solutions. The other thing we can do, of course, is that now that we've got both of these functions, we can graph them on our graphics calculator and see a couple of particular solutions so that we know if we're on the right track. We're going to need to use quite a few identities to solve this problem. So we've got 5 sine x plus 4 is equal to 10 times sine squared of x on 2. The first thing to notice that gives us an issue is that this is x on 2, or half of x, and this is x. We can use the double angle formula because x is 2 times x over 2. I find it easier to write that not using x over 2. I'm going to let u equal x over 2. So 2u is equal to x. That gives me 5 sine 2u plus 4 is equal to 10 times sine squared of u. And I'm going to follow that all the way through till we get down to our general solutions. Now the obvious thing to do here is to expand the sine 2u using the double angle formula for sine. There's only one thing to do there. It's not like cos of 2u. And looking at this, you can see that we're heading towards some kind of quadratic. The problem is that we've got sine and we've got cosine mixed up together, and there's not really much we can do about that. But I can spot that I'm heading for a quadratic, so I'm going to start by saying 0 is equal to 10 times sine squared u minus 10 sine u cos u minus 4. I've got a common factor of 2 in each of these terms, so we'll divide through by that, and we get 0 equals 5 sine squared u minus 5 sine u cos u minus 2. Now the problem here is the minus 2. Here I've got something that we can think about starting to factorize. So we're going to have something sine here, and we're going to have something sine here. In the middle, if we have a cos here, the cos times the sine is going to generate this thing here. But we don't want to have a constant on the end because we want the whole thing to equal 0. So what I want to be forcing in here is some kind of cosine squared term. And I can do that quite easily if I spot that that's where I'm going by using the Pythagoras identity. So if you look at that and you're kind of stuck on how can I factorize that, usually when we factorize, we're trying to simplify things, but here we actually want to go the other way around and replace this 2 with something initially messier. So we're going to do this. We've got 0 equals 5 sine squared u minus 5 sine u cos u minus 2 times cos squared u plus sine squared u. And this is going to work out quite nicely. So here we have, going really slowly, 5 sine squared u minus 5 sine u cos u minus 2 cos squared u minus 2 sine squared u. And cleaning that up gives me 3 sine squared u minus 5 sine u cos u minus 2 cos squared u. And we can factorize this. Now if that looks really awful to factorize, you might like to think about it like this. Just think of 3x squared minus 5xy minus 2y squared. How can I factorise that? Well, the nice thing in here is that these numbers are all primes, especially these two. So this will be 3x times x, and this has got to be 2 and 1. If we put a minus 2y here and a plus y here, let's look at whether that's going to work. So that gives me 3x squared plus xy minus 6xy minus 2y squared. So that's what we're after. I'm going to go back and do that with my trig functions now. So let's just put that into a little box here and keep on going. Okay, so this equals 3 sine u plus cosine u times sine u minus 2 cosine u. And that has to equal 0. So we're just about there. Either one of those things being 0 will make the whole thing 0. So either 3 sine u plus cos u equals 0, or sine u minus 2 cos u equals 0. So 3 sine u is equal to negative cosine u. This is going to be a tan equation. We get sine u over cos u is equal to negative 1/3. Or tan u, and I'll now write it back as x over 2. So tan of x over 2 is equal to negative 1/3. Working through this one, sine u equals 2 cos u. Sine u over cos u is equal to 2. So tan of u, which is tan of half of x, is equal to 2. So all we have to do now is the easiest of the three general solutions. We've got two tan equations to do. So alpha is the principal value of this one. So it's the angle whose tan is negative 1/3, which worked out to be negative 0.32175. That gives me a general solution of x on 2 is equal to n pi minus 0.32175, or x is equal to 2n pi minus 0.6435. Let's work through the other one. The alpha for this is the angle whose tan is 2, so that's the initial value, 1.01071. So x on 2 is equal to n pi plus alpha. X is equal to 2n pi plus 2.2142. Right, so we've found two general solutions, and these are all the possible values, right? So the two functions are equal at these x values. So let's just go on and find the ones that are in my graph. So if we substitute in n equals 0, what do we get? Well, we get x equals negative 0.6435. That's not one of the ones on my graph. And from this equation we get x equals 2.2142. So that looks good. We'll go and check that in a second. Let's put in n equals 1. That gives me x equals, so this is 2 pi minus this, so that's 5.6397. And this one gives me something outside the domain that's on our graph. I think I got that, or it might have been 0.5. Okay, so what we want to do now is just go up and check that these numbers make sense with the original picture. And you can see that they do. Okay, so this value here is the, let's just clean that big mess up. That value there, the last one, is 2.2142, and this one here is just a bit below 6.28, which is 2 pi, so this is 5.6397. So there you go. Let's just quickly go over the whole thing. The first thing we had to do was find the function, which was the red curve, and then we had to solve a problem investigating intervals where the red function was above the line y equals 6. Right, so we drew that in, and we found that that was the bit of the red curve that we wanted. In the second part, we had to link up the blue curve and the red curve and investigate whether two functions had the same value. So first we looked at the general solutions, and then we looked at a couple of particular solutions. Thanks for watching. Let me know in the comments if you've got any questions, or just send me an email.